Greetings. So, welcome to today's class. So, just a brief recap of what we have been doing till now. We have been looking at the class of linear time invariant causal systems, and we have essentially been analyzing its response using the transfer function, right? So, that's what we have been doing, and we were essentially considering various types of inputs and observing how to calculate the corresponding outputs and figuring out some characteristics of the system, by studying those outputs, right? So that's what we have been doing. So in today's class, we will look at one more representation. So to begin with, if we just once again to recap class of systems under study, if when we are dealing with linear time invariant causal dynamic systems, of course, we have been considering SISO systems to start with. So, and as we know by now, this class of systems is characterized by linear ODEs with constant coefficients, right? So that is the connection between the physics and the math. So the behavior of this class of systems, it can be characterized or captured by linear ordinary differential equations with constant coefficients. So if you consider this class of system, we can have two broad representations. So what are these representations? Okay, the first one is what is called as a transfer function representation. So that is what we have been looking at till now, right? So that is, in order to go to the transfer function representation, what did we do? We essentially considered the linear ordinary differential equation with constant coefficients. Then we applied the Laplace transform to it. And then we essentially applied zero initial conditions, then got the ratio of the Laplace of the output to the Laplace of the input. An alternative representation is what is called as the state space representation. Okay, the transfer function representation, we went from the time domain, which is a field of real numbers, which corresponds to a field of real numbers, to the complex domain, right, or the so-called S domain. But in the representation that we are going to study today, which is what is called as the state space representation, we are going to analyze the system response by staying in the time domain. Okay, so that is a big difference. But there are going to be some equivalence between the two representations, right? So because ultimately the system is one, right? So it is what it is. It is just that how we are expressing the system's governing equations and governing model and doing the subsequent analysis, right? So that's where the difference comes in. So essentially, we are going to look at the state space representation. So let me write down what this representation is, right? And then let's discuss further. So in the state space representation, we are not going to apply any transform like the Laplace transform. Okay, so see, one advantage that we got with using the Laplace transform and going to transfer function was that we converted an ordinary differential equation into an algebraic equation and did the analysis, right? So that's an obvious advantage, right? So but then the state space representation, we are going to essentially stay in the time domain, and the basic idea, behind the state space representation or getting the state space representation is to rewrite a nth order ODE as n first order ODEs. Okay, so we'll see how we do it and then what it gives us, right? So essentially those are some things which we will discuss shortly. So, but the central idea is to rewrite an nth order ordinary differential equation as a set of n first order ordinary differential equations. Okay, so that's what happens with the state space representation. Okay, so let us study it using an example, right? So and then we will generalize it. Okay, so let us consider our standard 1 degree of freedom mass spring damper system, right? So we consider the 1 degree of freedom mass spring damper system. So let's see how the state space representation comes about for this class of system or this system in particular. Okay, so let us consider this system. So recall that the governing equation is going to be mx double dot t plus cx dot t plus k times x of t equal to f of t, right? So this was the governing equation of the system, right? So from here, if we recall what we did to get the transfer function or the plant transfer function, the plant transfer function in this case was P of s. It is the once again the Laplace of the output divided by the Laplace of the input. In this case, it's going to be x of s divided by f of s. And if you recall, and then of course we had to substitute initial conditions to be 0, and we would have obtained the transfer function as ms squared plus cs plus. Okay, so that's what we would have obtained. And as we know, the value of n is 2 in this case, the value of m is 0. Okay, so that's something which we know, right? So that's why it's called as a second order system. Okay, it's a 1 degree of freedom system, but in the context of dynamic systems, okay, like the order of the system is essentially the order of the highest derivative of the output variable, right, in the governing ODE. Okay, so that's why it's called as a second order system. Now, what do we do? Okay, so what do we do in order to get the state space representation? Okay, so the first step is to identify as many state variables. Okay, so I will shortly define what these state variables mean. Okay, identify as many state variables as the order of the system. Okay, so that is the first step. So the first step behind getting the state space representation is to identify as many state variables as the order of the system. So what are these state variables? We will shortly get a physical insight into them, but let me define them. So before we go back to this example, the state variables are those variables whose knowledge at every instant of time, okay, completely characterizes the system response or the system's behavior. Okay, so whose knowledge at every instant of time completely characterizes the system. So that's what is called as a those variables are called as a state variable. Okay, so all right, so that's this set of variables is called state variables. So and the first step is that like we need to identify as many state variables as the order of the system. So in this example, n is 2, so we choose 2 state variables. Of course, the question one may also ask is that like how do we choose state variables in the first place, right? Is there a process to it? Well, we choose state variables based on some physical insight and some intuition also, right? We will realize as we go deeper into state space representation. And in fact, like when we go for vehicle dynamics and modeling, let's say cornering response, or let's say even braking response or suspension response, like we will write the ODE and also put it in the state space representation, during which time we will also choose the state variables intuitively. Okay, so we'll get a feel of it. So right now, let me come back to this example where n is 2. So in the example under study, we need to select 2 state variables. Okay, so in this example, let us choose the 2 state variables as okay. What are the 2 state variables? Let's say the first state variable is x1 of t as the displacement x of t. Okay, the second state variable x2 of t as speed x dot. Okay, so those are the 2 choices. Okay, so essentially these are the 2 state variables, and we form what is called as a state vectors. So what is the intuitive reason behind the choice? See, x of t is the displacement of the mass, right? Is it not? X dot of t is the speed. So what it means is that, like, if I know information about the displacement and speed of the mass at every instant of time, then I know pretty much what is happening to the mass spring damper system at each and every instant of time, right? Is it not? So that's why that's how we choose the two state variables as the displacement and the speed. Okay, and as I mentioned, when we start doing more examples, we will also get an intuitive feel of how we make these choices, right? So the state vector, the so-called state vector x of t, can be written in the following way, right? So it's going to be the two state variables stacked one below the other as a column vector. Okay, so that's how we write the state vector. Okay, so in this particular case, the state vector x is going to be comprised of the displacement x of t and the speed x dot of t. Okay, so that is our state vector. All right, so that is the first step. So what is the first step in writing the state space representation? We identify as many state variables as the order of the dynamic system under state. Then what we do is that we take the first derivative of the state variables. So we will see what this step brings us to, right? So as I told, like, the core idea behind the state space representation is to rewrite an nth order ODE as n first order ODEs, right? So what we do is that, like, we take the first derivative of the state variables and then, like, we work with it. Okay, so that's what is going to happen in this particular step. Okay, so we have two state variables x and x1. So what we do is that, like, first we take x1 dot, right? X1 dot will now be equal to x dot. So what did I do? I took the first derivative of both terms on 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 this first equation, right? This equation, right? So x1 is equal to x, right? If I take the time derivative on both sides, I get x1 dot to be equal to x dot. However, what is x dot? X dot is x2, right? So that's something we can immediately figure out from the second equation, right? Is it not? Okay, so that's what I'm going to use here. Okay, so x1 dot is going to become x2. So this is the central idea, right? So we essentially take the first derivative of the each state variable, and we try to rewrite it in terms of essentially, like the state other state variables and the input term. Okay, so that is going to be the core idea. Now, going to the second state variable x2, we take the time derivative of x2, which is going to be equal to x2 dot, and that is going to become x double dot. Why? Because as we notice from the second equation, we see that x2 is x dot, right? So now when I take the one time derivative on both sides, x2 dot becomes derivative of x dot. Derivative of x dot becomes x double dot, right? So that's why I get x double dot. But now I need to rewrite this x double dot in terms of the other state variables, right? And the input. So how do I do this? So for this, I go back to the governing ODE, right? So the governing ODE for the system is going to be equal to mx double dot plus cx dot plus kx equal to f of t, right? So that is the governing ordinary differential equation for the mass spring damper system. So what happens is that then I can rewrite this way, right? Mx double dot is going to be equal to minus kxt minus cx dot t, right? Plus f of t, right? I'm sure all of us can observe what's happening, right? So essentially, I rewrite like this. Now I come back to this equation. So I get x2 dot to be equal to x double dot, okay? And that's going to be equal to minus k by m x of t minus C by M x dot of t plus 1 by M, sorry, 1 by M f of. Okay, so that's what I got. All right. So now x of t is going to be equal to x1 of t, right? So as we already know, right? So because how did I get this from this equation? So we can see that x of t is nothing but the first state variable x1, right? Similarly, what is x dot? X dot is going to be the second variable x2. So you can observe what I am doing, right? As I just said, we are rewriting the first derivative of the state vector in terms of the other state variables and the input, right? And f of t is the input u, right? So that's something which all of us are already aware of, right? For this particular system, f of t is going to be the input, right? So what happens is, right, x2 dot becomes equal to minus k by m x1 t minus c by m x2 t plus 1 by m f of t. Of course, for the time being, I will retain f of t. I'm not going to rewrite that as u of t. So we can notice that we now have two first order ODEs. Okay, so we now have two first order ODEs. So the third step, see what are the two first order ODEs? You know, like if I can rewrite them. So this is first order ODE number 1. This is first order ODE number 2. So we can observe that we have rewritten the second order differential equation that we started off with as two first order ODEs. Okay, so that's what we have done. Now let's go to the next step. Okay, before I go to the next step, are there any questions about these two steps? So, yeah, please go ahead.
Sir, this equation LTI causal system, it has, as I understand, it has two representation, right? Transfer function representation and state space representation.
Yes.
So this state space representation is having some advantage over transfer function representation.
Okay, good question. We will discuss that. Okay, so the question is, like the state space representation have an advantage over transfer function representation? If I can put the same question in a different manner, right? So as a practitioner, right, I would want to figure out when I would want to use transfer function representation, when I would want to use state space representation. Is it not correct? So both representations have pros and cons, okay? And we will recognize their pros and cons as we go along in this, okay? So we will revisit this question. Please remind me of this question towards the end of the course. And we will also learn more features about these two representations when we go to automotive controls, okay? So both representations are useful, okay? So under what conditions we will learn them, all right? Fine. So let's move on. Any other questions before I go to the next step? Okay. The third step is to essentially group the first order ODEs to obtain the state equation. What is called as a state equation. Okay. Let's write down what this is, right? So we group the n first order ordinary differential equations to get what are called as the state, what is called as a state equation. Okay, so let me just be consistent. Okay? We call it a state equation. So how do I do that? The state vector is x, right? So the vector, the first derivative of the state vector x is x dot. Of course, I should also introduce notation here. So what is the notation which I am following? Typically the notations that I will follow here is that, like, if I have a lowercase character, right, with a tilde underneath it, okay, I am essentially representing a vector quantity. Okay, if there is no tilde underneath it, okay. So suppose if I use small a, capital A, and all, I am representing a scalar variable. Okay, a scalar quantity. Okay, if I put a tilde underneath a lowercase quantity, I am representing a vector. On the other hand, if I put a tilde underneath an uppercase quantity, I am representing a matrix. Okay, so this is the notation we will be following in this course. Okay, in this course and even in the subsequent course on automotive control. Okay, so let me repeat the notation. So if I use a character without a tilde underneath it, it doesn't matter whether it's lowercase or uppercase, they represent scalar variables. Okay, scalar parameters and so on. Okay, scalar quantities in general. So if we want to represent a vector, we use a lowercase with a tilde underneath it, unless otherwise I tell so. So that represents a vector. So in textbooks and all, you won't see the tilde, you will see boldface. Then some people will use an arrow above the character, right? So we are going to use a tilde. Okay. So since we can't do boldface font when I write, so I'm putting a tilde to differentiate. Okay, and when I use an uppercase with a tilde underneath it, we represent a matrix. In textbooks and type manuscripts, it will be an uppercase with in boldface, right? So that's the matrix. In textbooks and other sources, you will find scalars in non-bold italics font. Okay, whereas vectors and matrices will not be in italics font, but then like they will be in bold font. Okay, so that's the difference. Okay, so please remember this notation. All right. So you can immediately observe that why now I put a tilde underneath x, right? Because I am representing the state vector. Whereas under x1 and x2, I am not putting a tilde, right? Because these are scalar quantities. So the vector x dot is comprised of x1 dot and x2 dot. Now, what I need to do is that like I need to rewrite it as a matrix vector equation. Okay, so that's what I'm going to do. So I'm going to write this as something multiplying the column vector x1, x2 plus some column vector multiplying the input. Okay, so input is f of t. Okay, so that's what we have, right? So now I will write f of u of t. Okay, so this is the general form of a state equation. Okay, so what comes in, right? What entries come? So if you look at the first equation, we can see that x1 dot is essentially equal to x2. So if I want to get x2 from this equation, suppose if I do this, we can observe that if I multiply the row 0, 1 with the column x1, x2, I get x2, right? And then anyway, I multiply with 0, I am only left with x, right? So you can immediately see that I extract x1 dot equals to x2. Similarly, I now go to the second equation, right, which is this, right? Which is the second equation? It is this equation, right? So where I want to write what will be x2 dot, right? So if I want to write what will be x2 dot, so what do I do? Like we have to rewrite it in terms of x1 and x2, right? So what will happen? I have minus k by m multiplying x1, minus c by m multiplying x2, and 1 by m multiplying the input u, which is f of t, right? So if I write like this, you can immediately observe that we can get the answer, right? Get the same second equation, right? So that's what we have. Okay, and this equation, which is a vector matrix equation, is what is called as a state equation. So the state equation is nothing but the collection of all the first order differential equations that describes the evolution of the state variables. So you can see that we defined the state variables and then we took the first derivative of the state variables, right? And then that was used to essentially write the state equation. Okay, so that's all we have done. Okay, so if we go and look at this equation, this column vector x1, x2 is the state vector x. Okay, this vector is x dot. Okay, this is u. This 2 by 2 matrix, okay, is what is called as a state matrix. Okay, so this is what is called as the state matrix. Okay, and in general, it's an n by n matrix. Okay, n cross n matrix. Its size or dimension is n. So it has n rows and n columns. In this example, n was 2, so that's why we have a 2 by 2 matrix. Right? So I'm sure all of us can appreciate this. This vector is typically called as the input vector b. Okay, it is a column vector of dimension n. Okay, so it is called as an input vector b, and it is of dimension n. Okay, so you can see that there are 2 entries in this, right? And we essentially write the general form of the state equation in a closed form in this manner. So for linear time invariant causal systems, the state equation is written as x dot equals ax plus but, a b of u of t. Okay, so this is what is called as a state equation. So you can observe that this is point number 1. This is a vector matrix, vector ODE. Okay, so that's first point. And we have managed to rewrite an nth order ODE as a set of n first order ODEs, albeit in a vectorized form. Okay, so that's what we have done. So this is what is called, once again, as the state equation in general. And as I mentioned, the state equation essentially characterizes the evolution of the state variable with time, okay, given initial conditions and inputs. Okay, it's given some initial states, okay, initial conditions and inputs. Okay, so that's what the state equation. So the state equation can be used to essentially get the time evolution of the state variable, right? Given some initial condition and input. All right. So this is equation number 1. We are not yet done. Okay. So this is the first equation in the state space representation, because so you can observe that now in the state space representation, we have the input and the state variable, but where is the output? Okay. So if you recall, in the transfer function representation, we had the transfer function as the Laplace of the output to the input, right? So, but then we didn't have what to say. We essentially in the state space representation, we don't have the output yet appearing in the equation, right? So state equation only has the state variable and the input term, right? So now the question becomes, like how do we bring in the output into the picture? Okay, so the output y of t will be equal to, let's say we consider the displacement of the, okay, so so we know that the output is displacement, right? So recall that, okay, y of t is x of t. But then now, what is x of t? X of t is nothing but the first state variable, right? So even the output we need to write in terms of the state vectors and the input. Okay, so that's what we are going to do. Now, please look at what I am doing, right? So essentially, in order to get x1, I am going to take the dot product or the so-called scalar product of the state vector with the column vector 1 and 0, right? So if I do this, I'm sure all of us agree that we get the state variable x1. Okay, so you can immediately observe that we get the output to be x1. Okay, so this is what is called as the output equation. Okay, so the output equation in general, okay, relates the output to the state variables and the inputs. Okay, so that's what happens. And this vector is what is called, denoted by the vector c, is what is called as the output vector. All right. So output vector c, of course, this is the state vector x1. This is something which we already are familiar with. Okay, so this is what is called as the output equation. of course, some people, so essentially we can write as C dot X. Some people will write the same thing as the row vector 1 multiplying x1, x2, and they will call this as C transpose. Okay, so this is a very common notation which is used, but then I prefer this dot product notation, okay, because it's much more accurate, okay. So because, see, when we dig deeper into vectors, we have dot scalar product or dot product, cross product, and what is called outer product, or and then like other what to say, yeah, operations. But there is nothing like a transpose of a vector multiplying a column vector, right? So that operation doesn't exist, okay. So essentially, but that's a very common notation which is used, okay, in this domain. So in general, what will happen is that, like, if you consider the output equation in general, yes, please.
Sir, one query here, sir. We have
Ah,
derived the first equation which has this x parameter, right? So
ah.
x is anyways the input against which, sorry, x is anyway the output which we will be getting against the input u of t, right, sir?
Okay, okay. I think good
Yeah,
point.
but still,
So let
yeah,
me clarify. Let me clarify
yeah,
here. This x, okay. Unfortunately, in this problem, I use the variable x for displacement also. Okay, that is why I introduced the notation. This x is a vector. It's a state vector. This x is displacement. Okay, so that's a subtle change. Okay, so that is why I introduced the notation. So in fact, I could have called this as some z. I could have rewritten this equation as some mz dot plus cz dot t plus kz t, right? Where z is my displacement. Okay, then the input to the system will be f, output will be displacement z. Then the state vector will still be called x, but then now this will become z of t. I hope that clarifies the point, right?
yes, sir, yes.
So yeah, I think I should have pointed it out. Thanks for raising this question. It's an important question, right? So because that is where notation becomes very important. That x which I introduced in the state equation is a state vector, right? Whereas what I am introducing the output equation here specifically, right? That is only the displacement x of the system. You know, I think I should have used a different symbol. Maybe I'll remember this for the next time. Okay, like I will not use x once again. See, the character x is used with a boldface font or a tilde of representation uh, for denoting state vector. Okay, state variables are denoted by using the character x. Okay, so yeah, sorry about that confusion. I know, like in general, what happens is the following. The output equation in general is written as y c dot x plus dut. Okay, so this is the output equation in general. I'll explain what this dut is. Okay, dut term is what is called as a direct transmission term, but this is the output equation in general. Okay, so essentially, when we put both equations together, we get the state space representation. Okay, so that is the state space representation. So, and the DUT term, which is coming in, which we don't see in this example, it is what is called as a direct transmission term. Why is it called direct transmission term? Because the input is directly contributing to the output, right? Rather than going through the state variable. This will come into picture only when m is equal to n, right? That is the theory. But in this particular example, n was 2, but m was 0, right? M is less than n. So when m is less than n, you won't get the direct transmission. Okay, so that is why in this particular example, what we wrote down as output equation, we didn't see the du term, right? But I have to write it in general, okay? So the two equations put together form the state space representation. So let me write down the summary here. Hence, the state space representation of a LTI causal dynamic system can be written as x dot t is equal to a times x of t plus b times u of t, and y of t is equal to c dot x of t plus d times u of t. Okay, so that's what. All right. So this is the general state space representation. Okay, of this class of systems. Okay, so that's what we have. All right. So and we can see that there are four quantities, right? The state matrix A, the input vector B, the output vector C, and the quantity D, right? That appears in the direct transmission term. This set is what is called as a realization. Okay, so I'm just pointing this out to you. Like please remember this. So essentially, these are terms which we should know when we are dealing with the state space representation. So when people talk about state space realization, they are essentially talking about this A, B, C, D. All right, so that's what they're. All right. Okay. So just to recap the state space representation, once again, we stay in the time domain. We want to rewrite the nth order ODE as a set of n first order ODEs. So what do? Step one is identify as many as n state variables. All right. And then we form the state vector. Then step two is we take the first derivative of these state variables, rewrite them into rewrite them in terms of the state variables themselves and the input. Then step three is we group the first order ODEs to obtain the state equation, and then we also form the output equation, right? So then we get this form in general, okay? And the set A, B, C, D is what is called as a realization. All right. So is this derivation clear about the state space representation and the corresponding example? I hope it's clear, right? So any questions on this? All right. Okay. So I just want to look at one more concept in today's class, because we will encounter more state space representation as we go along. But I think this is also partially in response to the question that was asked by one of our friends, which can be used when, right? So we will learn all the answer to that question, right? In general, depending on which perspective we use by as we go forward. But before we do that, we also should answer this question, right? This is very important. So we should answer the question as to what is the equivalence between the state space representation and the transfer function representation, right? That's very important. So why is this important? Because ultimately we only have one system, right? So but then the question becomes, how do we handle the equivalence, right? So when we use one representation, how do we keep track of the concepts associated with the other representation, or some insights which we may be obtaining from the other representation? Okay, so it's important for us to answer this question, right? What is obviously there is an equivalence, right? So because at the end of the day, these are only two representations of the same system, and we should if we solve a problem irrespective of a representation, we should get a similar answer, right? So okay, so now let's look at the above equation, right? So first let us take the Laplace transform. Okay, we consider the state space equation. Let us take the Laplace transform of the state equation. Okay, so let's try to analyze that, and then we will do this one. Okay, let's take the Laplace transform state equation. Of course, I can apply Laplace transform even to vector linear ODEs. Okay, so this will become s times capital X of s, which will now be a vector, minus x of 0, which is once again the initial state vector, which will be equal to A times capital X of S. Of course, here capital X is not a matrix. Okay, as I told you, vectors will be in lowercase unless otherwise I tell it, right? So here, this capital X doesn't mean it's a matrix. It is just that the state vector indicated in the complex domain, right? Because our notation for complex valued functions was that we use the transform function, we denoted by the corresponding uppercase character, right? So that's what we are doing here. All right. So this is what we do, right? So then we apply zero initial conditions. So because in order to get the transfer functions, we take all the initial conditions to be zero. So what happens? This x0 becomes zero. Okay. So in fact, this is one important difference. So in fact, using the state space representation, one can analyze both the free response and the forced response. Okay. Whereas transfer function representation, implicitly, we are only analyzing the forced response. Okay. As we can observe, we have identified one difference between the two. Right. So now let's go ahead. We apply zero initial conditions. Let's group the terms. So we will get Si minus A times X of S. What is this A? I will shortly explain. That is going to be equal to B times U of S. A is nothing but the identity matrix. Okay. So in this case, if for let's say we have the mass spring damper system, it is a 2 by 2, second order system, right? So I becomes a 2 by 2 matrix. Okay. So then what happens? The identity matrix for dimension 2 of the second order system just becomes a diagonal matrix whose diagonal elements are all 1 and off diagonal elements are all 0. Okay, so that's the identity matrix, right? I'm sure all of us are familiar with this. Okay, so this is something which we know. And then what we do is that, like, assuming that the inverse of Si minus A exists, we essentially get X of S to be equal to Si minus A inverse B times U of S. Okay, so that's what we have. Okay, by taking the Laplace transform of the state equation. Okay, so I hope this step is clear. We will shortly be applying it. Now, let's say we take the Laplace transform of the output equation. So take the Laplace transform of the output equation. What do we get if we apply the Laplace transform of the output equation? We just have a very simple equation, right? Y of S is going to be equal to C dot capital X of S plus D times capital U of S, right? So that's what we are going to get. Okay, so that's the result we will get by taking the Laplace of the output equation, as we can see there. Now, what we do is that, like, we are going to substitute for X of S. Okay, so X of S is Si minus A inverse. Okay, times U of S. Right, plus anyway we have this du of S, right? So how did I get this? We just substituted this into this, right? So we just substituted X of S here, right? So that's what we did. So once I did this, you know, like we get this equation. Now we are almost done. So then this implies that through this derivation, we have Y of S to be equal to C dot Si minus A inverse E plus D times U of S. Okay, so that's what we have. Okay, so this is a very important equation. Why? Why am I saying that this is an important equation? Please recall that the relationship between the input, Laplace of the input and the Laplace of the output under zero initial condition is through the transfer function, right? So if you compare both these equations, what do we get? The one within the square bracket is the Planck transfer function, right? So the Planck transfer function is C dot Si minus A inverse B plus D. Okay, so one can clearly see an equivalence between the state space representation and the transfer function representation, right? So given the realization A, B, C, D, one can derive the plant transfer function P of S. Okay, so that's what we have. All right. Okay, so I hope this derivation is clear, right? So we can see the relationship between the state space representation and the transfer function representation. Now, if you look at this, in fact, if you recall, the plant transfer function was n of s divided by t of s. What were the roots of d of s called as? What are the roots of d of s?
Zeros.
Poles, right? Very good. Okay. And if you look at the right hand side, in fact, we will see that if I want to calculate the inverse of a matrix, right? How do I calculate the inverse of a matrix? I form what is called as the adjoint, classical adjoint or adjugate of that matrix and divide by the determinant of the matrix, right? That's how I calculate the inverse of any matrix, right? Is it not? Okay. So you can observe that on the right hand side, I will get something in the numerator, but in the denominator, I will get determinant of Si minus A. I'm sure all of us agree, right? Due to this fact, correct? So I will have some factor in the numerator nonetheless, right? So in the denominator, I will get determinant of Si minus A, right? So you can immediately, and if I want to solve the roots of determinant of Si minus A, what are the roots of determinant of Si minus A called as? How do I get the roots of a polynomial in S? I just solve determinant that polynomial equal to 0, right? So if I solve the equation determinant of Si minus A equal to 0, what are the solutions called as? Eigenvalues of the matrix. Very good. Okay. So they are what are the called as the eigenvalues of the matrix. Okay. So this also establishes a very important equivalence between the two representations. Okay, let me write it down. So for the class of systems under study, that is linear time invariant, causal dynamic systems, and under some conditions, for the class of systems under study, under some conditions, we will not worry about these, what these conditions are right now. Okay, and under some condition, right? There is an equivalence. Okay, the poles of the transfer function and the eigenvalues of the state matrix are one and the same. Okay, the eigenvalues of the state matrix A okay, are same as the poles of the transfer function. P of S. Okay, so this is a very important. Okay, this is another equivalence between the state space representation and the transfer function representation. Okay, so that's something which we need. All right. So, by the way, some people call the state space representation as an internal representation because we are going from the output to the input through the state variables. Whereas transfer function representation, since it directly relates the output and the input, we call it as an external representation. Okay, so this terminology is just for your information. Okay, so yeah, so we'll use them when required. All right. I will stop here for today. And I'm going to leave you with a couple of homework problems. But before I write down the homework problems, like, are there any questions about what we studied today?
Sir, I still don't understand that like output equation. Why are we writing like that?
So see, the idea is to essentially rewrite the output in terms of the state variables. Okay, in this case, the output happens to be the displacement x. Okay, right? So unfortunately, the symbol for displacement which I used coincided with the symbol for state variable. Sorry about that. Okay, but think about X as displacement. Okay, let me not call it as X, displacement. Okay, and it so happens that the first state variable X1 is displacement, right? As we can see here, right? So what we do is that, like, we rewrite the output in terms of displacement. Okay, rewrite the output displacement in terms of the state variable X1. But this is the form we want to get to. Okay, so that's why we wrote it as a vector multiplying the state vector. Okay, so you can see that if I how do I get X1 from the vector X1 and X2? I need to extract X1 from the vector X1, X2, right? So I take the dot product with 1, 0. If I do the dot product with 1, 0, I get X1, right? So that's how we write. And that's the general form.
Yeah. Yeah, how we are getting that, I can understand, sir, actually. But why are we doing this? That is my question. Like,
That is because the state space representation has two equations. Okay. See, if you look at the state represent, let's say the system per se, right? As I told, see, unfortunately, I use the same symbol X. Okay, I think I should not have, but anyway, it's a lesson for me, right? So if you look at it in general, a system has an input U of t, right? And it has an output Y of t, correct?
Right.
So in the state space representation, so in the state space representation, we have this extra variable X of t, okay, which is internal to the system. So we go from the input to the output through the state variable, okay? But if you look at the state equation, it doesn't have the output, right? Does it? Right? So
yeah.
The representation is not complete. The state equation has a relationship only between the state variable and the input. It doesn't have the output variable. So that is why we needed this output equation to complete the state space representation, right? So that is why if you look at this, what we are doing is that in the state space representation, maybe it may be useful to visualize it like this. We go from the input to the state vector, and then from the state vector to the output. Okay. Yeah.
Yes. Okay. Got it.
All right.
Okay.
So
yeah.
that is why some people call it as an internal representation, right? So we are dealing with something which is internal to the system. Okay. Whereas plant transfer function, we directly write the output of input. Okay.
Yeah. Okay. Thank you.
Okay. I hope this provides some more insight and feel into this representation. Okay.
Right.
So we will get more idea as we go along, right? So please bear with me. Like when we do more examples, I'm sure we will essentially get more insight into this. Okay. So what I want you to do is the following. Okay. Derive the state space representation of the following systems. Okay. So system, these are things which we have already done, right? So where we have derived the plant transfer function. Okay, I'm not giving you anything new. Okay, so this is system number 1. The transfer function is 1 divided by s squared plus 3s plus 2. And in the second case, it is y double dot plus 3y dot plus, this should be 2y, not 2ut. Okay, 2yt should be equal to u dot plus 3ut. Okay, so here the 0 is introduced at minus 3. Okay, so please derive the state space representation for both these systems. All right, and calculate the eigenvalues of the state matrix. Right. So I leave this to you as homework number 3, which you can submit by this Sunday. Okay, I will post the Google form. So calculate the eigenvalues of the state matrix in each row. Okay. Is it clear what should be done? And then we will continue from here in the next class. Okay. Sorry, I exceeded the closing time by a few minutes. So let me stop recording.